so you can reply the lecture if needed. Okay, seems okay. So today's lecture will be focused on molecular dynamics. So the quite common abbreviation is MD. So if you somewhere see MD in the context of drug design, that's always the abbreviation for molecular dynamics. It is quite a hugely used method nowadays. And in contrast to, for example, molecular docking, which we already covered in our lectures, molecular dynamics is something, it's a method which simulates processes which are running in time. So you are adding a time aspect to your simulations. So that means you can also study non-equilibrium processes. So systems which are far from equilibrium, and you can study how and if they get somewhere close to the equilibrium. Okay, when I say time aspect, you should have an idea what are the times, how long are the processes which we are able to simulate by molecular dynamics nowadays. So typical molecular dynamics simulation today is usually from tens of nanoseconds to hundreds of nanoseconds. That's very typical, yeah, tens of nanoseconds to hundreds of nanoseconds. Sometimes, for some purposes, it's enough to do a shorter simulation, just hundreds of picoseconds, for example. That means the tenths of nanoseconds. Sometimes, if you study complex processes, for example, like protein folding, I'll have the example later, you might need to study even longer than hundreds of nanoseconds, for example, over 1 millisecond. The problem is that the molecular dynamics is always very computationally exhaustive. Yeah, so to give you an idea, a molecular dynamics simulation, that's a simulation that can be running for several days before you get your results, and the longest simulations can take weeks or even months, yeah, because before you are able to simulate these time scales. So why is it that molecular dynamics simulations are so computationally exhaustive, such CPU demanding? The reason is this is because everything in the system is flexible. Yeah, maybe you remember when we talked about molecular docking, the process when we try to predict the mutual pose of ligand inside of a receptor. We also talked about flexibility, and then in that lecture I told you that quite often we are doing docking in such a way that ligand is flexible, so it can conformationally change, but the binding site is usually rigid, or in the most explicit scenario, you attach flexibility to only few amino acids, side chains of few amino acids in the binding site. Yeah, and we also explained why, because if you would add the flexibility to the whole protein, for example, for docking, it would take very long to simulate the process. Yeah, because the time needed for the simulation, the energetic evaluation based on the force field, it scales exponentially with the number of freely rotatable bonds, with the degrees of freedom. So this is the cost. So with molecular docking, we try to avoid this problem by treating the protein usually as rigid or flexible to a very limited extent. But in molecular dynamics, we can no longer use this approximation, because in molecular dynamics, we want to study the system in conditions which are as close to the real system as possible. Yeah, imagine typically we will be simulating, let's say, a ligand in a protein in water. Yeah, and there everything is flexible. Oh, I already said that the systems which we are studying, usually we try to do it quite realistic. So let's say we have our protein, the protein has a ligand bound, so we will put it into a solvent, yeah, because normally in biological relevant environment, the proteins are in solvent, in water, right? Okay, we can set up the ion strength, yeah, so we can put there the correct concentration, let's say, of sodium cations, chloride anions, potassium cations, and so on. We can balance pH of the solvent. We can control temperature, but also pressure. Yeah, therefore we can set up the proper density of water or other solvent we would like to use. So we are trying to do it really realistic. Molecular dynamics, don't be confused. It's a very general method, so it's not used only in drug design. Yeah, of course, drug design is of our interest. So in drug design, you can, for example, simulate a binding of ligand to a protein, to its receptor, or you can simulate the unbinding. You can just reverse the process and you can evaluate how much force you need to apply to the ligand to make it go away from the binding site, and from that you can tell something about the ligand protein affinity. Yeah, so if you need bigger force, it means that the affinity of ligand to the protein, to the binding site, is quite high. Yeah. It's in drug design. In drug design, you can use also molecular dynamics to study, for example, the protein folding. Yeah, what is it, protein folding? You know, of course, that protein can be described by the primary sequence of its amino acids. Yeah, but it doesn't tell you anything about the shape of the molecule. Yeah, because the primary structure is then being folded into the helices and beta-pleated sheets and other structural motifs of secondary structure. Then you have the tertiary structure and quaternary structure of the protein. And how you can determine these structures of the protein, of course, experimentally, yeah, by X-ray crystallography usually, or solution NMR, similar methods, cryo-EM, of course. And you can also compute it by doing something which is called homology modeling. I think we have covered this in the previous lectures. And you can also use molecular dynamics to simulate protein folding. So I will have an example, but just briefly speaking, you just take the amino acid sequence, you put it into water, and you run the simulation long enough to give the protein time to organize itself into the correct spatial arrangement and spatial structure. Yeah, because what it is, what are the forces which usually drive the protein folding? Usually these are ionic interactions. Of course, hydrogen bonds are very important, disulfide bonds, and also the hydrophobic interactions. So all of these take their part and make the protein fold in some way. The other thing is, if this simplified simulation can be good enough to simulate the structure of proteins, because we must not forget that how the proteins are produced in real life. Yeah, they are produced like by adding one amino acid by one on a ribosome. So that's completely different process. Yeah, than having the primary sequence and putting it into the water. And very often there are also proteins which help other proteins to get their 3D shape. You know, these are called the chaperones, for example. Yeah, but nevertheless, methods of using molecular dynamics to simulate somehow the protein folding are also used. And it's another application of molecular dynamics in drug design. In drug design, we can also use molecular dynamics to generate conformers. Yeah, so the conformational analysis to generate conformers of small molecules. Yeah, I will have another slide in this lecture explaining the advantages of this approach of using molecular dynamics to generate conformers. Okay, that was about drug design, but as I said, molecular dynamics is very broad method, so you can use it to, for example, simulate physicochemical processes. So you can simulate melting, dissolution, adsorption, phase separation, and many others. There are, for example, methods. Just to give you an example, you know how partition coefficient P, what it is and how it's being determined. Yeah, so partition coefficient P is the concentration of compound in octanol divided by concentration of the same compound in water. Yeah, usually know this parameter as a log p, so the logarithm of partitioning coefficient. You can, of course, measure this, yeah, by just partitioning the compound between two immiscible phases, octanol and water, and you can simulate directly this process by molecular dynamics. So you'll prepare a system where you will have two separated phases. Try to draw it. Okay, so you will prepare your system in a way that in the top half you will have the octanol. In the bottom part you will have the water, and then you put your molecule of interest, your compound, just equally to both to the space. So let's say we will have 5 molecules in this. Of course, in practice you'll have much more. Okay, 5, and then this is your starting system, and then you will let the system develop by molecular dynamics. That's the simulation. And after a certain time, you will evaluate how many molecules, how many instances of this compound is in the octanol phase and how many are in the water phase, and you will just do the division. So this is just simulating the partitioning, and this is really some methods have been successfully developed to predict log p based on these molecular dynamics simulations. We can use molecular dynamics in material science, so we can study nanomaterials and many other things. Okay, so what is it exactly? So we already talked about what molecular dynamics can be used for. Now let's talk briefly, not in a detail, but just very briefly about the principles it builds upon. So important thing is that molecular dynamics is most often based on force fields. Yeah, so it's the common situation which you already know. So it's based on molecular mechanics. Yeah, and molecular dynamics is not anything else, just numerically solving the Newton equations of motion for a system of n atoms. Yeah, so you have the n atoms. The n can be very huge. In a typical system, again, let's stick to our example: ligand in a protein, in a cubic box of solvent, you can have several thousand to tens of thousands of atoms. Yeah, so this n is very typically tens of thousands. Okay, so at the beginning, you address this problem. You have to address this problem. So each particle in the system, yeah, each atom in the system has to be given a velocity, yeah, initial velocity. And when I say velocity, I mean velocity as a vector. So not only a scalar like the number, how fast, but also the direction. Yeah, so the vector velocity. Okay, how this is done? It's from the thermodynamics. So it's done based on the temperature and so-called Maxwell-Boltzmann distribution. So just to give you a taste, if you have a lower temperature, let's say 100 kelvins, the most particles of the system will have this velocity, which is relatively low. Yeah, some particles will also have lower velocities. Some particles will have higher velocities. Yeah, but this is the average, and this is the shape of the distribution. If we now increase the temperature, and by the way, I said that we want to study the process in biological relevant conditions. So the typical temperature would be 300 kelvins, yeah, which is like 27 degrees Celsius, something like that. Yeah. So here we see the curves for 200 kelvins and 400 kelvins. Yeah, and you see what is the effect. So if you increase the temperature, of course, the average velocity, yeah, so the velocity which has which the most particles have is shifting to the right, yeah. And also the other effect is that the distribution is being broadened, yeah. So this is how you attach the initial velocities, yeah. The initial velocities are basically the forces which act on each particle, yeah. So we have some forces which can be also evaluated from the force field, like energy calculations. So you have the velocities or forces, doesn't matter much how you call it, acting on each particle. Then you let the system to develop for a small duration of time, which we will design delta t, yeah? And then you will evaluate to which new positions the particles have moved in this time. So we will get new particle positions at the time t, which is our time 0, plus delta t. Yeah, and it all is driven by solving this very simple equation, like force is mass by acceleration. Yeah, so you know this equation from your very basic physics lessons. Okay, so now let's talk about the delta t, the time step of the simulation. This is this slide. So I said that the typical simulation, the MD simulation, let's say it's usually tens of nanoseconds, hundreds of nanoseconds, the longest ones 1 millisecond. Yeah, so we are somewhere here, yeah, in this area. But how short has to be the time step? Yeah, the time step, a typical time step in molecular dynamics simulation is usually 1, 2, or 4 femtoseconds. Yeah, so okay, let's say that our simulations are typically nanoseconds, so 10 to minus 9 nanosecond, but the time step is like a million times shorter. It's 10 to minus 15. Why is this so? This situation on the left part of the figure is a good situation. So let's imagine we have like two particles for now, and this is the velocity, yeah, the velocity or the force which is acting on this particle. So you will keep the system develop in time. So now the time is running like this way, yeah, and this particle will move away from the first particle, like to here and to here. And this is my time step, yeah, from here to here is the time step. And because this particle, let's say B, moves away from the equilibrium position, which this is the equilibrium position, it will have the tendency to go back. Yeah, so we have some force which has been created and forces the particle to go back to the equilibrium position. And this force is quite okay, so the system can happily develop. But on this right hypothetical situation, you see that the initial velocity, the initial force of this article B is the same as in our first situation, but the difference is that we will let the system develop for a much longer. It means that the time step is not this short as in our first example, but it's this short or long. What it means that the particle B will get too far away from the equilibrium, and there will be much bigger force, yeah, which will try to pull the particle back. And actually, if your time step is too big, this force can be such high that it would, in theory, if you just do simple calculation, like the velocity is like the acceleration divided by mass, yeah. So you will end up with speeds which are greater than the speed of light, which is impossible, of course, and your simulation will crash. Yeah, so this is the situation which we do not want. This is This means that the time step is too long. So typical time step is usually really in femtoseconds, and we are asking this in the final test. Yeah. The time step also depends on what effects or what occasions you want to study in your system. Yeah, so because you can simply imagine that different processes take typically different times. Yeah, so if you look at the molecule, so for example, a stretching of a bond, yeah, it's somewhere between femtoseconds and picoseconds. Yeah? So if you want to cover these, and if you want to know something about bond stretching, your step, your delta t has to be just below or at the femtosecond level, so you have a good enough resolution. Yeah, but in some cases, maybe you are not interested in the stretching of the bond. Maybe you want to be more focused on the motions on a larger scale, like if we look at the other side of the spectra, like for example, rotation of some side chains, or opening of some parts of the protein based on the hinge bending and so on. So different processes can take different typical time, and your time step has to be shorter than the fastest process you would like to study. So again, typically 1 to 2 femtoseconds. By the way, the fastest process, which is normally studied, is the bond stretching of the bond of hydrogen to something, yeah, to some heavy atom. Yeah, because it of course depends on the molecular weight of the particle. So because the energy is the same and hydrogen is has the low molecular weight, so it will oscillate the fastest. Yeah. Well, on the contrary, if you have two heavy particles like carbon and nitrogen here, the oscillation will be much slower, or significantly slower. This is, by the way, the basis of how you get in infrared bands, yeah, in your infrared spectrum. Yeah, because the stretching of this bond will be somewhere different in the infrared spectrum, the stretching of this bond. Yeah, so the stretching of bonds between hydrogen to some heavy atom are the fastest. So if you are not interested in these fluctuations of positions of hydrogen, you can increase your step to 2 femtoseconds. Yeah? On the contrary, if you want to study these fluctuations as well, keep your time step to 1 femtosecond. All right, so that was about the time step. Now I would like to talk shortly about the system boundaries. Yeah, because we want to simulate like real processes. Yeah, but we cannot do it normally, because think about a situation you would like to study a real life thing. So for example, you take 100 milliliter beaker, you put it into, you pour water into it, and you put your protein in the solution, yeah, in 100 milliliters. So how many particles that would be? Yeah, so it can be 1/10 of kilogram, like 100 milliliters of water, 1/10 of kilogram. Yeah, so it will be many moles. Yeah, so it means what 1 mole is 10 to the power of 23 particles. Yeah, so that's not possible to simulate 10 to power 23, which would be one mole. So we have to cope with this problem somehow. So one possibility is to make the system very small. Yeah, like free boundaries. So how you do it? You just put a single molecule of interest, like single molecule of protein, of, for example, into a cluster of molecules of solvent. Yeah, and you pretend that this is basically in vacuum. Yeah, so you have your, I'll try to draw it. Yeah, so you have your molecule of interest, and then you will have your molecules of solvent all around. Most typically it will have a sphere shape, your system, yeah, and basically you are pretending that your system is in vacuum. Yeah? And there is nothing which could prevent the molecules of solvent to go in all directions. Yeah? So if you keep the system developed for a significantly long time, all the molecules will just go away, and basically this can be interpreted like evaporation of the solvent in vacuum. Yeah. So this setup is sometimes used, but it can be used only for simulations which are very short. Yeah. If your process of interest happens on smaller time scales than the evaporation of the solvent, which would be the end stage of this simulation. So more often we use rigid boundaries, which you can imagine in this way. You basically change the color of my pen. So what you do, you basically apply an artificial force field barrier around the system. Yeah, so you have the initial system, and you apply a potential artificial potential barrier. So as soon as a particle goes anywhere close to the barrier, there will be a force which will try to push it back. Yeah, so the particle goes close, and there is a force which will try to push it back. So you feel that this is not very natural, yeah, because normally we do not have a force, yeah, which pushes something back. But this can be unphysical and can introduce some artifacts into the simulations. Yeah. All right, so the last approach how to cope with the boundaries of the system is so-called periodic boundaries. So periodic boundary system, PBS, often abbreviated, periodic boundary system. Okay, so periodic boundary system, or you can see the abbreviation PBC, periodic boundary conditions. So what is it all about? It's quite a smart method how you can eliminate the boundaries, actually. Yeah, so the trick is that you have your basic unit. So imagine this is your basic unit in which you have everything you are interested in. So in our example, it will be the ligand in a protein, ions, molecules of solvents, everything. Yeah, and then you let the computer to replicate this basic cell in the directions of the axis x, y, and z. Here on this simplified scheme, I have replicated only in 2 axes, yeah, but normally this would be a cube, so the basic unit will be replicated in 3 axes, x, y, and z. Yeah, and the trick is that the particles in the basic cell do not interact only with themselves within the cell, but they also interact with their images. Yeah? So with the particle, with the image. So for example, if a particle goes here, it can interact with particle which is here. Yeah, so it's a cross-boundary interaction. So, and this replication is done like into infinity, which means that actually you do not have any boundaries. So we have solved the problem with boundaries, yeah, because here the boundaries were free. That's no good because we have evaporation only for short processes. Here we had rigid boundaries, so artificial potential barrier, which is not very how it should be. Yeah, so we solved this problem that we eliminated the boundaries. There are no boundaries at all. So now you probably are questioning yourself how this computation can be done if the system is so large. In theory, it's endless system because the cell unit is replicated into infinity. But the trick is that actually the other units are just images of the first unit. So for example, what happens, and I think I have it on the next slide, yes. So imagine that we have a particle here in the primary unit, primary cell, which is getting close to the boundary of the cell. Yeah? And it has the tendency to go from here to here. But what happens? We can let it go, we can let this particle go, because in the mirror image, which is this cell, this particle, when this one leaves the basic cell, this one will enter the basic cell. Yeah? So this is how the roughly constant number of particles is kept in each cell, even though you have no uh, boundaries. And the energy of the system can be evaluated quite efficiently because there is symmetry. Yeah, that's the key. Yeah, so in theory you have infinite number of copies of the cells, but there's always a symmetry. So it's enough to compute the particle, the interactions of particles within the cell, and you know the interactions of all the particles in the system. So it's a periodic boundary condition, and this is really the most used scenario nowadays. Okay, so this was a talk about the boundaries. Now let's talk a little bit about the solvent, how we can simulate the solvent. This is quite similar to how we can simulate solvent in normal force field minimizations, molecular mechanics, and so on. So two basic possibilities: either you can have implicit solvent or explicit solvent. Implicit means that actually, in fact, that there are no solvent molecules. So if we stick to water, which is biologically relevant, there will be no water molecules, and you will just set up the constant, the permittivity constant, to be the same one which is known for the water. Yeah. And so these are fast models, but less accurate. Yeah, so these are just some of the abbreviations, like Cosmo model is very famous and quite often used today, PCM, polarizable continuum model, and so on. So these are implicit solvent models. More precise are explicit solvent models. So now we have real particles or real molecules of the solvent, for example, waters. Yeah? So this simulation is obviously slower because when I said that in a typical system, again, our example, ligand in protein in a solvent box, in a box of water. So usually in this system, I said that the number of particles, it's usually tens of thousands. Yeah, and out of this, 1,000 particles or 2,000 particles can be the protein, and the rest it's water, molecules of water mainly. Yeah, so that's the question how we play it. Either we have thousands of particles or tens of thousands if we include explicit solvent. Yeah. Okay. So to make the calculation with explicit solvent possible, we usually use some constraint models for the water. So in one of the slides, I said that everything is treated flexibly, but it's not true very much. We actually already saw two exceptions. Let me go back. One exception was this. So basically, when we were not interested in the fluctuations of the hydrogen atoms, we can fix them in space. Yeah? So that was first exception. So making hydrogens fixed. Yeah? So these are not flexible if you want to speed up simulation. And the second biggest exception is are the models of the solvent. And so, for example, for water, the most often used model is tip 3P model. Basically, the 3P means that it's based on three parameters. Yeah? And the thing is that the distances between OH, and the angle, it's fixed. Yeah, so the molecule can move, it can rotate, it can anything, but the distances and the angle are fixed. So it lowers the degrees of freedom in your system and speeds up the calculation significantly. Yeah? If you imagine that this molecule is repeated tens of thousands times in the system. All right, so just to give you a taste how the tip 3p modal parameter looks like, basically what you need to define is the distance between OH, which is 0.9 something angstroms. You have to define the degree, HOH, which is 104 degrees and something. Then you have to define the strength of the bond. Yeah. So this is the strength of the stretching. So the higher the number, the less stretching. This is the strength of the angle bending, and then you have the Q's, which are charges. So charge on oxygen will be obviously negative, and charge on hydrogen will be obviously positive. Yeah, and this is how the model is constructed. Okay, so now let's talk about how the MD is computed. Let's talk about the so-called statistical ensembles. So for a real system, we most often use this so-called NPT ensemble, which is also called isothermal isobaric ensemble. That's for the production stage of real systems. So which means NPT means that we have fixed number of particles, that's the n, it's fixed, and we are controlling the pressure, obviously usually setting it to one bar, 1 atmosphere, yeah, and we are controlling the temperature, usually setting it to 300 kelvins, something similar. Yeah, so this is what we used most often for the production stages. We'll talk a little bit more about the stages later. But there are some simplified ensembles. So for example, NVT is the ensemble where we control only the number of particles. That's always, yeah. So N is always controlled, it's always fixed, because you cannot change the number of particles in your system. It has to be the same. So N is always controls, and in NVT we control the number of particles, the volume, and temperature. The volume of the box and the temperature. So what it means, so we have constant number of particles and we control volume and temperature. It means that basically we cannot control the pressure, yeah? Because if you change volume, you have the same number of particles and you change the volume, let's say you decrease or your volume of the box is decreased. Oh, sorry, the other way around. So if you have the temperature and you set up to certain value, yeah, and you want to increase the volume of your box. If you increase the volume, the temperature would be lowered, yeah, by thermodynamical principles. So to prevent that, you have to modify the pressure. Yeah? So if you increase the temperature and you want the volume does something, and to compensate this, the pressure has to be changed. Yeah, so you cannot control all of the parameters like volume, temperature, and pressure at the same time. So you always control two of them, and the third one is free to change. Yeah. So because there are always fluctuations. Yeah, because for example in this NPT ensemble, you just set up the value for pressure. Yeah, you set up the value of temperature, but they are oscillating around the set value. Yeah, and the oscillations means that if the temperature goes little bit up, then the volume has to be adjusted, and so on. Okay, so these two ensembles are used quite often. We also can use the so-called microcanonical ensemble, which is without any temperature and pressure control. So we are controlling only the number of particles which is set, the volume of the system, and E, that's for energy. So the energy is set, but we don't care about the temperature, pressure, or volume. All right. So how can you imagine a molecular dynamics, how it's practically done? Molecular dynamics, it's usually separated into several stages, yeah, which can be given some name. The stages in different softwares are have different semantics, so you can write them down in different notations, but usually it looks like something like this. Yeah, so this would be the name of the phase, which can be anything you want, like this means is for minimization. This is the duration of the stage, like 10 picoseconds, and that is this is the temperature. Yeah, so temperature 0 means in many MD engines means that we are basically doing the energetic minimization, a normal force field energetic minimization, and we have no temperature, we have no velocities of the particles. Yeah. So this would be the minimization. Then we usually do so-called heating. So because we start with temperature 0, which is just normal force field minimization, and then we want to slowly increase the temperature of the system. So this notation means that for 200 picoseconds, the temperature will be varied from 0 to 300. Yeah, so over 200 picoseconds, we are increasing the temperature for 0 to 300. Yeah, so slowly heating. Then we usually have some equilibration phases. Yeah, so here we have 3 in this case, equilibration stages. And equilibration basically means that you have to let your system develop long enough so it can get somewhere close to the energetic minimum, to the equilibrium state. Basically, the idea is to remove the artifacts which might be in the original system. Yeah. So in this case, we have equilibration under the NVE ensemble. NVE means we are not controlling the temperature, we are not controlling the pressure. Yeah. So we just enter the time. Then we have another equilibration stage. This time it will be NVT ensemble. It means that we are controlling the temperature. So we enter the time and temperature, which we are controlling. Yeah, and then we have NPT equilibration, means we are controlling pressure and temperature. And you see that we set up the temperature 300 kelvins in this case, and the pressure, this one would be in kilopascals, right? All right, and then after these equilibrations, which are just meant to equilibrate the system, get it to the equilibrium state, then you start the production phase of molecular dynamics. And this is the most important. From the production phase, you then record the trajectories. So trajectories means like files which contain the positions of all atoms, how they change in time, and you record it. You record the trajectories, and by analyzing the trajectory, you can just analyze the system, its properties, and so on. Yeah. So in this case, it's a 5 nanosecond production phase, which is quite short nowadays. Usually tens of nanoseconds, hundreds of nanoseconds are done. Yeah. Just talking about the trajectories, one can imagine that the trajectories can be very huge files. Yeah, because if you have like tens of thousands of atoms and you have to record position of each one, I don't know if you ever had a look when you downloaded, for example, a PDB file from a PDB database. It usually has few hundreds of kilobytes. Yeah, but imagine that you have to multiplicate this for each frame. Yeah, so usually the trajectories are saved. Let's say if you have 10, for example, you save it at the rate that you save each picosecond. Yeah, for example. So that's a huge amount of frames which have to be saved, and the trajectories are usually then in hundreds of megabytes or even gigabytes. So it's quite extensive for the disk space, these simulations. All right. So practical aspects. So how do we do the molecular dynamics? What is the workflow? So first we have to prepare the system. Yeah? I already said that the system we try to make it as realistic as possible. So let's say we have our ligand in our protein, we have some molecules of solvent, yeah, and the molecules of solvent can be organized in different shapes. It can be a sphere, it can be something similar, or it can be cubic, or just a box. Yeah? Of course, if we use the periodic boundary conditions, which I talked about before, you would have to use this rectangular shape, or in some softwares you can also use orthogonal shapes, but definitely not spheres, yeah, because you need to replicate this along the axis. All right, so we have the ligand, we have the protein, we have the molecules of solvent. So this time we are using the explicit solvent model. Then you use ions. Yeah, there are special utilities which can add ions for you. So you just determine what is the desired concentration of sodium ions, potassium ions, chloride anions. Usually you chose the values which are relevant for biological environment, of course, for example, our body. Yeah, and then the system places them reasonably. So for example, first Na plus cations will be first placed, for example, close to amino acids which have carboxylate in the side chain. Yeah, so it will be like COO minus Na plus. Yeah, and then when these amino acids which are sitting on the surface of the protein will be bound, yeah, then the ions will be placed randomly into the bulk solvent. Yeah. Okay, so this is the system. Then you do the minimization, like normal force field minimization. You can do this in advance, or you can do it as a part of the molecular dynamics. So if you do it as a part of molecular dynamics, so this is it. So this is a force field minimization. It's not a molecular dynamics in the strict speaking, because here you have temperature 0, so no velocities for the particles. Oh wait, then you do the equilibration of the system. So you have some phases which will do the equilibration, and you are just monitoring some important properties of the system. And once they are settled and they start to oscillate around some equilibrium value, it means that your system is equilibrated, and you can, from that point, you can start your production phase of molecular dynamics. So what are the parameters that you can be following to determine whether your system is equilibrated or not? So one of them is RMSD. So it's like root mean square deviation, which tells you how big is the change between positions of the atoms between one frame and the following frame. Yeah. So you see that in the beginning, typically it's quite a huge jump, yeah, and then you oscillate around usually a value 1.5 up to 2 angstroms. Yeah, it means that here it's not changing. Yeah, just I want you to understand this notation, this graph. So here, for example, if we have no change, it's oscillating around this value. It means that we are like, let's say, 1.75 angstroms from the original position. Yeah, but we are still 175 plus minus something from the original position. So actually from here to here, the system is not changing much. Yeah, in this area, there is a huge change. The jump means a change, and here we have some kind of equilibrium state. So you can check the RMSD of the protein itself, of the backbone, or usually you watch the backbone. I will show you later. Or you can also watch the parameters like energy of the system. It should be equilibrated as well. You can watch the density of the solvent. Yeah, so if your system is well equilibrated, the density of the solvent should be somewhere around 1 gram per cubic centimeter. Of course, the normal value. Okay, so when your system is equilibrated, you start the production and you collect the data and you save them to so-called trajectory files. Then when you have the trajectory files, which as I said might be several gigabytes of information, yeah, you just load them into some kind of software and you do some analysis of the trajectory files. So just to give you a brief taste how these trajectories are being analyzed, basically you can select distance between two atoms, for example, which is important for you, angle, you can see how it develops in the time. More general terms which are used for the analysis are RMSD and RMSF, and it's important to understand the difference between them. So let's first talk about RMSD. RMSD means root mean square deviation meant of atomic position. So we already had this parameter in the equilibration stage. So RMSD is a way how to measure how one state of the molecule, means one frame, differs from the previous state, previous frame. Yeah. So the RMSD can be calculated from all atoms in the system, but more often it's to take it from, let's say, the protein, and because of course you are not calculating comparing the position of solvent atoms. That would be a nonsense. Yeah, but usually you focus on the protein in our example, and in the protein very often you focus only on the backbone, yeah, and not the side chains, because the side chains are always flexible. The side chains are always moving, so they will have higher RMSD values. Yeah, so you can focus on the on the backbone, which you can just define like CONH, C alpha, or you can just focus on C alpha atoms. Yeah. So the RMSD parameter tells us, when we just look at the graphs, when something is happening. So when, that's the important word which you should remember. Yeah. So if you look at the graph and the value of RMSD in certain time frame is low, it means nothing is happening. Yeah. So if you have only minor oscillations like 0.9, 0.1 angstrom, it means that nothing significant is happening in the structure. And if you have larger jumps, like in the units of angstroms, 1, 2, 3 angstroms, it means that something is happening, something is going on in the system, and you have to have a look what is going on. Yeah. So the RMSD evaluation tells you when. It helps you to locate the frame of the MD when something is happening, but it doesn't tell you what is changing. Yeah. So this is just a formula. It's nothing special and no need to memorize it, but just explain. So you calculate the RMSD. Okay. You just have the positions of the atom. Let's say now let's have it for one atom. Yeah, so just choose one atom. So let's say this one from the carboxyl, the upper one. So we have a position in the frame, U. Yeah, the position can be defined as a vector in Cartesian coordinates. Yeah, then you have its position of the same atom in the frame V, which might be next frame. Yeah, then calculate the distance between the two positions. So this is how we do it normally, like one vector minus the other vector squared. Yeah, and then you do this for all the atoms in the system. So the sum runs from 1 to the n, when n is the number of atoms in the system. So you do compare the positions of all couples of the protein for all atoms, basically. Yeah, or the subset of the atoms, for example, the C alpha carbons, and then you divide it, because it's like mean square deviation, and this mean means that you normalize it by the number of the atoms. Yeah, so it's an average displacement, average over all the atoms. So it's average over the number of atoms. Yeah. Okay, and the other parameter is RMSF, root mean square fluctuation. And this parameter, the formula looks quite the same. I'm going to start with the formula. So here with RMSD, it was normalized on the number of particles. Yeah, so it was a mean over the number of particles. But here in the RMSF, we have it normalized by time. Yeah? So here we do something similar. We compare the position of one atom, yeah, and we do the comparison. So now we have time of frame 1, frame 2, frame 3, frame 4, and we calculate basically the RMSD of this one to this one. So this is our reference. We calculate the RMSD from this one to this one, this one to this one, this one to this one, and then we average. But this time we do not average by number of atoms, we average by time. Yeah. So what we are getting, this RMSF, is like time averaged value, and it tells you it can be defined for every atom in the system alone, or for a ligand, for example. But the thing is that you get only one value for the whole simulation. Yeah. So this is the basic difference. The RMSF is a measure of flexibility. Yeah. So it helps you to determine not when, but which atoms of the system experience significant movement. Again, significant movement would mean RMSF at several angstroms. Or if the atom is rigid, not moving in the whole simulation, the RMSF will be like tens of angstroms. Yeah. So once more, the RMSD tells you when. Yeah. And you have the RMSD value is each for each frame, and the RMSF tells you which, and you have one value for the whole simulation. So now the example to give you a better understanding. So for example, here we are measuring, this is the trajectory analysis, and we are calculating the RMSD, root mean square deviation, and you see that we have value. RMSD has value for each time frame. Yeah, so on the axis you will have the time, or the frames, doesn't matter. Yeah, frames or the time, and you see how it develops. Yeah, so this is our original minimized structure. Then you start the simulation, huge jump, then some modifications, and let's say from here we might consider it, let's say, equilibrated. Yeah, it does not change much. What is the difference between these two lines? So the bottom one is if you calculate the RMSD only for protein, and for the protein you will calculate it only for C alpha atoms. Yeah, so basically representing the backbone, how the backbone is moving or not moving in time. If you do the same but calculate the RMSD taking into account all atoms, it means the backbone plus the flexible side chains, of course you will always get a higher value. Yeah. So be careful please, this RMSD this time is in nanometers, so 1 angstrom is 1/10 of a nanometer, so basically here we have 1 angstrom. Yeah, 1.5 angstroms. So as I said, the well-equilibrated protein, the RMSD value should be somewhere oscillating somewhere around 1.5 up to 2 angstroms. So this is quite in concordance with the value. All right, so this is the RMSD, tells you when something is happening. So then when you see a jump, like here we go a little bit down significantly, you know that something is happening here in this slide, and you have to analyze what's going on. So on contrary, the RMSF, so again we have the analysis of the RMSF parameter, root mean square fluctuation. So it tells me not when, but what atoms are undergoing some change. And we have one RMSF value for the whole simulation. Yeah, so here on the X axis, we no longer have time because we have just one value for the whole trajectory, for the whole simulation. But here we have the numbers of atoms. So this is like the RMSF factor for atom number 0. Yeah, or you can have it. You can calculate for it for individual amino acids. Like you average the RMSF of the atoms of the amino acids. Yeah. So this graph tells you, for example, that this atom number, and you'll read the number here, was very flexible. This one was very flexible during the whole simulation. On contrary, these atoms at the bottom are very rigid, not moving at all during the whole simulation. So RMSF tells you which atoms are moving, not when, but which atoms. So once again, here we have the answer when something is happening, but we don't know what is happening. And here with RMSF, that's the contrary actually, because you know which atoms are moving, but you don't know in which frames. Yeah, because it's an average. All right, so we can now talk a little bit about molecular dynamic applications. Yeah, so on the first slide, I gave you an idea what MD can be used for. It can be drug design, but all other things like material science and so on. So just a few comments on these. I said that the molecular dynamics is very favorable when you want to study or the conformations of your, let's say, small molecule or even proteins. Okay. What's the difference? Because of course we can do normal energetic minimization. So imagine you draw a 3D structure of your molecule, like small molecule this time, and you try to minimize it by the force field. But what can happen to you using this normal energy minimization based on the force field is that you will end in so-called local minimum. Yeah. So imagine that you draw a molecule in your software. The software generates some 3D coordinates which are quite reasonable, but definitely not minimized. Let's say here, yeah. And let's say you just do the normal energetic minimization, which is usually based on two methods, like the steepest descent algorithm or conjugate gradient algorithm. And the algorithms try to decrease the energy. They go like this. This increase of energy is quite small, so they can overcome it, and oops, and you end up in this local minimum, which you don't know it's a local minimum because you just know from your simulation, from your energy minimization, it seems that it's a minimum, but you don't know if it's a local or possibly there exists some global minimum, which is even lower and the more correct 3D structure of the molecule, the biologically more relevant one. Yeah, but your normal algorithms, which we use for energy minimization, can never go from here to here because it's improbable, because the energetic barrier from here, if you want to go from here to here, you would need to overcome this energetic barrier. Maybe I'll draw it. So the highest energetic barrier which you have to overcome is this. Yeah? And this is too much to overcome by the normal energy minimization algorithms based on force field minimizations. But what you can do, you can use the molecular dynamics, because in molecular dynamics, you can, of course, as I already said, control the temperature. And the temperature is then projected on how much energy is in the system. So if you slightly increase the temperature of your system, you will be able to overcome the energetic barrier, even such high as this one. So the molecular dynamics will help you to go from here to here to here, and then you can happily fall down and find the global minimum. So the conformation analysis based on molecular dynamics are very often used, especially when you want to be sure that you have explored the conformational space of your molecule. Okay, so let's say you would like to know something about your protein. Yeah, it's another implication of molecular dynamics. So you can have your protein, your 3D structure, and you would like to know which parts of the protein are flexible and which are not. So what you can do, you can run the simulation of your protein, usually in a box of water, yeah, and then of course you do first the equilibration. So once your RMSD is set around some equilibrium value, it means you are equilibrated and you can start recording. Yeah, so again you see that well equilibrated protein RMSD value is somewhere around 1.5 angstroms usually. Yeah, and then you can calculate the RMSF, so root mean square fluctuations of each, let's say, amino acid, and it will tell you which portions of the protein are flexible and which are rigid. Yeah? So these blue and green regions have lower numbers, lower values of RMSF, means that they are rigid, and these red ones are, on contrary, highly flexible. Yeah, so it can help you with the design. I also said that molecular dynamics can be used to predict the 3D structure of proteins. That is the protein folding. Yeah? Definitely, this protein folding takes very long time. Yeah, so see that we start from something like this. We have the simulation running, and now we are not in the range of hundreds of nanoseconds. We are in microseconds, so three orders higher. Yeah, so it really takes long. Yeah, and if we keep the system developing, we can observe formations of some secondary structures. Yeah. So this is of course heavily dependent on how good is your force field, because your molecular dynamics, basically molecular dynamics is just based on the force field. So if your force field does not describe your protein well, you cannot expect good results. And on a video, I think later I will show you how much difference it makes if you change the force field for like protein minimization and protein folding simulations. Right. Some special cases of molecular dynamics we are also asking this slide in the final test. So I said that the whole molecular dynamics is based on force fields, so it's molecular mechanics. It's true, of course, because we have very huge number of atoms, so we cannot do quantum mechanics, but there are methods. Imagine that you are simulating, I don't know, your ligand in protein, and this protein is a metal enzyme, for example, so it has a metal ion in the active site, and imagine that your ligand is bound to the metal in the protein, in the binding site. And the problem is that very often the common force field do not describe well the energy of the bond of a normal atom, let's say ligand, to the metal. So you can get really weird results. So how you can cope with this problem is that you select few bonds, for example, 1, 2, 3 bonds in the system, which you know are really important for your result. And these will be treated based on quantum mechanics. So more precisely, much more precisely, but also much more computationally demanding. Yeah, so you can afford this only for a few bonds. So 1, 2, 3 bonds in the system will be simulated by quantum mechanics, and the rest of the system by molecular dynamics. So these methods are then called QM/MM molecular dynamics, quantum mechanics, molecular mechanics. Another approach how to speed processes up are to use so-called coarse-grained force fields, which then give rise to coarse-grained molecular dynamics. So the most known example of coarse-grained force field is so-called the Martini coarse-grained force field. How it goes? So basically, the idea is that you are using particles which are more coarse-grained, so bigger than the normal atoms. Yeah? So for example, there is the Martini force field has parameters for lipids. Yeah, so if you have a lipid, imagine you want to construct you want to study a protein by molecular dynamics. You want to study a protein which is a protein, a membrane protein. So you should put it into a phospholipid bilayer. Yeah, okay. So this is the lipid. Yeah, so you have the phosphate. Yeah, this is the OH groups of the glycerol, and then you have the esterification of by the fatty acid. Yeah, so this is the fatty acid. So you could be simulating like using normal force field. It means that each atom would be a single particle. Yeah, but if you want to speed things up, you can like represent these. Okay, because these 3 carbon atoms. Okay, let's say we do not want to simulate as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 balls or spheres, but we just want to create one bigger sphere with some specific properties. Yeah, so this sphere represents 3 units of carbon chain. Yeah, and we have this repeated units. There is another sphere defined which will represent the ester moiety, and there is another sphere defined which will define the phospho part of the molecule. Yeah, so this can speed things up, because remember that the speed of the computation is like exponentially dependent on the number of particles. So if you decrease the number of your particles, you speed up your simulation significantly. Yeah, maybe more more for you, more obvious it will be for protein, because you know the amino acids very well. So in the case of protein, yeah, we can simulate like the CONH, so the backbone, like one sphere, then you have another sphere for the C alpha atom, and then you have different spheres for the side chains. Yeah, so again, by defining different spheres with different properties, we can spare or decrease the number of particles in the system. And we also talked about one principle. Basically, using the tip 3P water model is a similar thing, yeah, because we are fixing the molecule of water, the distances and the angles. So basically, we are treating a molecule of water as a single sphere. So that's what we have already covered in the tip 3P model of the water. So this is it. So coarse-grained molecular dynamics. Yeah, if you need to study really big systems like membranes, phospholipid membranes, proteins, which are very large, or you need very long simulations. Yeah, because if you have a normal protein and you want a normal length simulation, you can use normal force field and have each atom as a particle. But if you need to prolong, have a very long simulation, then your only hope is to use this coarse-grained to speed things up. Okay, another special case of molecular dynamics is a method which is called SMD, meaning steered molecular dynamics, which can be used to study the binding or unbinding the ligands. Yeah, because there are 2 ways how you can do it, how you can study binding of a ligand to a protein, to a binding site. Either you can have your protein, you can put it into water, you can put a significant concentration of your ligand around the protein, yeah, so many molecules of the ligand, and you can just wait and wait and wait until one ligand gets into the correct tunnel, gets into the binding site and binds. Yeah, but this usually takes very long, and usually very long simulations are needed. So that would be the normal molecular dynamics. But to speed things up, again, you can use this SMD, which basically means that, let's now describe it for the unbinding. Yeah, so you have the ligand bound here, so you can have this from a docking study or a crystallographic study, and then imagine the protein looks like that 3 possible tunnels are leading from the binding site to the solvent, like tunnel 1, tunnel 2, tunnel 3, the blue, red, and yellow. Yeah, 3 directions, and you don't know which one is the real tunnel, how the ligand gets inside. So what you do, you start your MD simulation, but not equilibrium simulation, but you apply some external force on the ligand. So you just define a center of mass of the ligand, let's say it's here, and you apply a force, a very tiny force in this red direction, let's say. Yeah, and the ligand starts moving in that direction, in the red direction, because you have applied the external force. Yeah, and then you switch off the force, and the ligand will keep moving if it's feasible. Yeah, then you do the same for the blue direction. So you apply external force, small external force for some time in this direction, and then you do a third independent simulation, and you apply the force in this yellow direction, and then you evaluate the trajectories and you calculate the energy, the force actually, which was needed to pull the protein out in this direction, in this direction. And of course, the direction for which you needed the smallest external force is the real one. Yeah, because normally systems go with low energies. Yeah, so by this steered molecular dynamics, it means that we are steering the movement of the ligand by applying external force. You can use it for studying the binding or unbinding of the ligand. Okay, this is, I think, one of my last slides before some demonstration videos, which some of these I will play now and comment, and some of them you can play at your home. Okay, so some MD records. So this is taken from the Wikipedia page, maybe not well updated, so you can check for yourselves, but just to give you a taste. Yeah, because normal situation is that we are simulating, okay, our typical system will be a ligand, protein, solvent. So typically thousands or several thousands or tens of thousands of particles. Yeah, and the typical time would be, let's say, hundreds of nanoseconds these days. Yeah, so 100 nanosecond, for example. So these are the records. Yeah, so for example, the largest system ever simulated by molecular dynamics contained 10 to the power of 12 particles. So not 10 to the power of 4, as this is typical, but 10 to the power of 12. Yeah, but you see, of course, you need special equipment for this. So the computation utilized 10 to the power of 5. It means 100,000 CPUs, yeah, or the cores. It was in 2017. Or another interesting experiment was the simulation of the full satellite tobacco mosaic virus. So it is a virus, yeah, which affects the tobacco plant, yeah, and this virus, the complete virion, has like 1 million atoms, yeah, and they were able to simulate it for 50 nanoseconds. So very nice thing. Yeah. Okay, and let me go to the last point, which is the longest simulation. I'm not sure if it still holds true, but as an example, it's quite good. So the longest simulation, yeah, the number of particles was normal, like thousands, but the length of the simulation is extraordinary, because normally we are doing hundreds of nanoseconds. If we go like 3 orders higher, we have microseconds, and they had milliseconds. Yeah, so it's getting close to the real time. Yeah, so for example, if you watch F1 racing, the difference between the cars can be in milliseconds. So we are already getting close to the real time, real life scales, I would say. All right, so these were the records, and now just to give you a taste, or maybe before I play these videos, so I'll try to recap the lecture. And one important thing I forgot to mention is about the time and the CPU and computational exhaustiveness together. Yeah, so just to give you a taste. So because we already talked about several methods. So for example, with molecular docking, you know that a normal computer, let's say 4 cores on a CPU, so docking of one molecule into a protein, it took you, let's say, 30 seconds or one minute. Yeah. So to give you an idea, the molecular dynamics cannot be done on a normal computer. You need at least supercomputer with or at least a working station with, let's say, 32, 64 cores, something like that. Yeah. Or another possibility is, and it's quite trendy today, is to use GPU computing. Yeah, so now you are using graphical cards, graphical processing units, GPUs, to do the calculations, like all the NVIDIA stuff and so on, and which is really quite helpful because the speeds you are getting with GPU accelerated algorithms are much larger than with CPU based algorithms. But to give you a taste, so if you have a normal system like ligand, protein, explicit water solvents, let's say 10,000 particles. So with our software, which we are using on a normal CPU-based computer, 64 cores, for example, you can simulate, let's say, maybe 20 nanoseconds a day. Yeah, 20 nanoseconds a day. So you need a day to simulate 20 nanoseconds. If you use GPU accelerated, you can simulate even hundreds of nanoseconds, let's say 200, 300 nanoseconds per day. But just to give you an idea. All right, so the recap of the lecture, you should definitely remember what is molecular dynamics. So it is a method which adds the time aspect to the simulations. You should know that molecular dynamics is based on force fields usually, so on molecular mechanics. You should know something about the time scales, so how long or what processes, how long processes are simulated. That is typically from let's say hundreds of nanoseconds to the record is millisecond, but microsecond would be quite typical at the higher end of the longiness of the simulation. Yeah, you should know something about the boundaries, that most often we use periodic boundary conditions. You should know something about that the systems are simulated as close to the real systems as possible. So we have water, ions, temperature control, pressure control, and so on. You should know how the how the outcomes are being analyzed. So the trajectory analysis by RMSD and RMSF, the basic difference between these two guys. And then in the final test, we are asking about some of the special aspects of molecular dynamics. It was, for example, the QMMM molecular dynamics. It was the SMD, steered molecular dynamics, and similar things. And now I would like to switch to the videos. I'll just show you something. This introduction to MD, you can show it for yourself. So I will just show you two of them, the donepezil binding to acetylcholinesterase and protein folding. And at home, then you can have a look at the rest of them. For example, melting of ice is very nice. Okay. So let me go. Okay, so I will comment it. So let me pause it for a little while. So here, this is the protein, this is the acetylcholinesterase. By the green amino acid residues, this is the binding site, highlighted binding site. And here we have the donepezil, which is the ligand which should really bind to the active site. Now the ligand is somewhere outside of the protein. These tiny spheres around, these are molecules of water, so we are using explicit solvent. Please, we are, of course, picturing only the heavy atoms, so oxygen, yeah, the hydrogens are not visible. And please do not be mistaken, the molecules of water are not just around the ligand, they are all around the system, here, around the protein and so on. But for clarity purposes, they have visualized the water molecules only around the vicinity of the ligand. So what happens now? So watch this upper chart, upper graph. So here we have time on X scale and we have RMSD. So you see that something is happening, yeah, because the RMSD is changing, yeah. So I already told you that RMSD tells me when something is happening. So huge changes here because we have a huge motion of the ligand, yeah. You can also watch the time scale, 3 nanoseconds by now. And you see that here at 3 nanoseconds, it kinda stopped changing the RMSD. So here you could think that the system is already equilibrated, or the better said, the binding is finished. Yeah, it looks like that, but that's not the case because the ligand is not in the binding site yet. So I'll speed the video a little bit so we don't have to wait that long, and we will try to catch the important frame in which the significant change happens. So let's observe it now. Yeah, do you see it? So now, okay, a great change was here. The ligand was moving into the binding site. Here, it already seemed that everything is finished. We have equilibrium system, but that was not the case. If we waited long enough, then in the 9.7 nanoseconds, something like that, something happened. I can tell by the change of the RMSD. Yeah. So once again, the RMSD tells me that something happened. Yeah, but I don't know why. I have to look in the 3D representation. And what happened? Yeah, it's the movement of this part. Yeah, which this part as it's now. And I will skip here. Yeah, it changed the position. So this was the movement. And from now on, it will be again stable. And now they show us the, sorry, I want to go back. Oh, no, I want to go back. Okay, let me just skip to the end of the video. Okay, now they show us the comparison between the pose which we obtained by the molecular dynamics, which is the yellow one, compared with the crystallographic pose, because obviously they were studying ligand which is known. Yeah, so you see that the it's very well overlaid with RMSD 1.4 angstroms. The difference between the crystallographic pose, the wild one, and the one you got by MD simulation of the binding. Yeah. Okay, so this was the first video I wanted to show you, and the second video is the protein folding. I told you that MD can be simulated to used to simulate the protein folding, and I also said that the outcomes of the molecular dynamics are heavily dependent on which force field you use. Yeah, so we have different force field, like Ember is more suited and more optimized for proteins. Charm is also optimized for proteins. OPLS is rather used for small molecules. Yeah. And we have different versions of the force fields. So we will see how it makes the difference or not. So this is from a publication, and they have only used a very small protein. Yeah, but be careful. I just wanted to show you this is important. I said that the protein folding simulations takes very long times. Yeah, so the video which we will see is like cut it, and we see the time from 0 to 10 nanoseconds, and then just the ending part of the video, which is 990 to 1000 nanoseconds. So the whole simulation was 1000 nanoseconds. It means 1 microsecond. Yeah. Okay. It's only a small protein to be able to see something. Yeah. So I don't know if it's maybe hexapeptide, decapeptide, something like that. Yeah. So not typical protein. And you see how things go. Yeah. So they keep it simulated, different force field, and I just want you to show you the take-home message here. The organized secondary structures are highlighted. So here we have, for example, the beta sheet, yeah, highlighted. Yeah, and I just wanted to show you, okay, I'll stop it right here, that we have 9 different force fields and 9 different results. Yeah. Okay, so let's say this one is quite similar to this one, but completely dissimilar to this one. Yeah, and completely dissimilar to this one. Which one is correct? You don't know. Yeah, you have to predict the structure experimentally. So just please have this in mind, that molecular dynamics, as well as other methods, are heavily from molecular mechanics, are heavily dependent on the force field which you use, and you have to be sure that your force field describe your system well. Okay, so this is for the lecture. So I will now switch to the Teams window to see if you have some questions, either in chat or on microphone. I'm happy to answer. Yeah, otherwise there are 2 lectures remaining for you. Both of them will be held by Dr. Kučerová. The first lecture will be on some databases which can be used in the drug design, and the last lecture, which will be in the new year, will be about some case studies from the drug design based on molecular modeling. So 2 lectures remaining. Slowly start thinking about the term when you would like to take the examination test. For Jose, of course, you have the project here with the MOE software. You can be practicing either tomorrow or whenever in the public computer room, as I put into the email today. Nejin is doing the open source exercises. So once you have them ready, just consult with us, and based on these you will be getting a credit, and then you can write the examination test, which is a written test in Moodle. Okay, so thanks for your attention. I will wait here for a few more minutes if you have some question. If not, thank you for your attention. So I'm switching my microphone off now, but I'll be here for a few more minutes. So if you have something to ask, just go forward. Otherwise, thank you and bye-bye.
Excuse me, I have a question regarding the examination that you have just mentioned, please.
Yes.
You talked about open sources that I have to work on. Unfortunately, I'm a little bit unclear about that. So if you can let me know.